time. And as we do that, as we look at that, what is the distance that we are talking about in this part of the problem? 1 revolution. So how far is that? We're going to go along the circumference of the circle. I mentioned in part 1, circumference is 2 pi r. But when we get to r, we know it's 10.2, the radius or the length of that second hand, divided by the time, and it's going to go around in 60 seconds. That's how long it takes the second hand to go around the clock. So now we have an answer that is, this is 10.2 centimeters, and I'm going to carry my units through the problem so I know that I'm heading in the right direction. So when I multiply that out, I'm going to get 2 pi times 10.2, or 20.4 pi centimeters over 60 seconds. And when I tap that in the calculator, this is going to be approximately 1.07 centimeters per second. So that is the, let's see if that showed up in, yeah. Right here we are. Yes, it showed up. Still on the board. It's still in range for your view. So notice we ended up with centimeters per second. That is one of the types of velocity units for linear velocity which we are expecting. So there we go. How about angular velocity? Alright, recall we're looking for radians per second or revolutions per second. And so I will probably show you both of those. So right now we're sitting at 1.07 centimeters per second. Notice centimeters is in the numerator along with the 1.07. I'm going to put it over 1, and that will give me seconds in the denominator. So I'm going to do some sort of operation to change that, and we'll do it first in radians per second. Alright, the problem doesn't specify which kind that you're trying to find, revolutions per second or radians per second. You have your choice, but I'm saying I want to know angular velocity in radians per second. So I'm starting down that path, and I notice seconds are in this expression and in this one, so I don't have to mess with seconds. But I have centimeters that somehow I have to transform to radians. The way I do that is I'm going to take 1 radian, and remember, a radian is the same as a radius. A radius is simply picked up and put on the circumference of the circle, but it is the same in distance. So 1 radian in this problem is 1 radius or radian. The lengths are interchangeable for radius and radian, 10.2 centimeters. Do you see how this equals 1? I can multiply anything by 1 and it doesn't change the problem, just the form. So 1 radian, or 1 radius, is the same as 10.2 centimeters in this problem. So this is just a big fat 1. We call it a unit multiplier. Why did I choose that? Well, I knew I had to get from centimeters to radians, so I took a unit multiplier with centimeters and radians in it. And centimeters will cross out, and then we have left 1.07 radians over 10.2 centimeters. So now when I divide 1.07 by 10.2, I get approximately 0.104 radians per second. And that is an answer for angular velocity, radians per second. What if I wanted to do revolutions per second, and I'm in radians per second? Let me show you how to change it. 0.104, and that's radians in the numerator, seconds in the denominator times 0.104 radians per second. So I want to go to revolutions per second. So how do I get from radians per second to revolutions per second? It turns out that seconds is okay, so I don't have to mess with that. But how do I get from radians to revolutions? So I have to come up with a unit multiplier where the numerator equals the denominator, and one of those has radians and one has seconds. So I'm going to put radians on the bottom so it'll cancel, and revolutions on the top. So how do I make it equal to 1? Well, how many radians are in one revolution? One revolution is one path around the circle, and that is 2 pi radians. So when I multiply that out, I'm going to get on the top, radians is canceling, 0.104 on the top, 2 pi on the bottom, and that is in revolutions per second. 0.104 over 2 pi revolutions per second. And when I divided that on the calculator to clean it up a bit, I got 0.017 revolutions per second. Alright, so this is another type of angular velocity, and notice how I let the units actually guide my path. Alright, I think that I will ask you to do one more in your comp book, and I will teach it in the morning just to see if you can follow these steps in another problem. Alright, so in this problem we are going to have a Ferris wheel. Don't ride on it. Some of them have proven to be dangerous in the news we hear of. Alright. So we have a Ferris wheel, and we'll say that the radius of the Ferris wheel is 90 feet. I'm sorry, 50 feet. 50 feet. So this Ferris wheel, it goes at 1.5 revolutions in 1 minute. So it takes a minute. It's a pretty large Ferris wheel. So it's going to take in 1 minute it goes around once and then half of another revolution. So what I want you to find is, this is already angular, but I want you to change it to radians per minute. We did the other one in radians per second, but we'll do this one in radians per minute. That's also proper angular unit. So let's also look at finding, so this is going to be an angular calculation. Let's find a linear velocity as well for this object, and for someone out here in the bucket. So I want that to be in feet per minute. And so if you're riding a fairly large Ferris wheel, how many feet do you think you would go in 1 second? It's kind of hard to visualize 1 minute of riding, how many feet you would go. But they're going fairly fast. I'm just guessing, but maybe 15 feet in a second. Would you really go that far? So I kind of keep in my mind, so when I finish this, I'm going to change it to feet per second and see if my answer is even reasonable. So I'm guessing, I don't know, 15 feet per second. Maybe it doesn't go that fast, or maybe it goes faster, but this is a sort of an idea that makes a little bit of sense to me. If I'm riding in this bucket, that in a second I would cover 15 feet. So we'll see when we calculate it out later. So in your comp book, I want you to take this information and do this process and tell me what you get tomorrow. All right, best of luck. See you then.